When we deal with measured numbers, we're used to using our significant figure rules. And so if we have, for instance, 100 and we add it to 100th, the sum result is not going to be what our calculator gives us, it's just going to be 100. Our calculator will call it 100.01, but we'll just call it 100 because this quantity is insignificant compared to this quantity. Now, strictly speaking, significant figure, we're actually talking about the size of the error in the numbers. That's what we're comparing. But even if we had an exact number, let's say that 2 million is an exact number and all the digits are significant, and we add it to 1, our answer is 2,000,001, but it's still pretty reasonable to say, well, this is just about equal to 2 million. Well, that lends us to a useful insight that in general, when we ever add a large number and a small number, the result is approximately equal to the large number we started off with. And this can lead us to some very useful simplifications. So say we're dealing with some polynomial expressions. And we'll start by considering where we have x to the 4th plus x squared and take the square root of that whole quantity. Now, if x is large, we take a large number and we take it to the 4th power. That's going to give us a very large result compared to taking that number and raising it to the 2nd power. So, on the whole, this sum is going to be about equal to the larger of these, the x to the 4th. And so if we take the square root of x to the 4th, we get x squared. So this whole term right here should be approximately equal to x squared. Well, let's see if that's true. We'll go ahead and try it out. So let's say x is equal to 100. Hopefully that will be large enough for our purposes. Well, in that case, this will be a very large number. This will be comparatively small. And so 100 to the 4th power plus 100 to the 2nd power, we take the square root of that. We get 10,000.5, very close to that anyway. And that is very similar to what we would get if we had just taken our x and squared it, like we said here. In that case, we would get 10,000, or 100 squared. So by making this approximation, we obviously didn't get, if we go by this, it's not exactly the same, but the difference is only, plus a half, and that's very small compared to the actual quantity of 10,000. It might also be the case that x is relatively small. So for instance, it might be a fraction. Well, if it's a fraction, if it's x is equal to, say, a half, so we have 1 and we've divided it by 2, then in this case, where we raise it to the 4th power, we're going to be dividing by 2 4 times. But when we raise it to the 2nd power, we're only going to be dividing by 2 twice. So this is going to be a comparatively larger number than this number. And so when we add these together, going off of our rule that a small number plus a large number is about equal to the large number, should be about equal to x squared. So for our radical expression, so whatever is under the radical, we're going to say that's about equal to x squared. And we take the square root of that, and we get about equal to x. So this whole thing should be about equal to x. Let's see if that works out. So let's say that x is something like 0.2, about a fifth. All right, well, if we punch it into our calculator, square root of 0.2 to the 4th plus 0.2 squared, we get about this number, 0.20396. Well, that's about equal to 0.2, which was our x. So in this case, it's worked out again. We've gotten a rather close answer using our approximation, which obviously requires a lot less calculation. Now, when we're solving equations, there is a problem that we run into. We saw that we had 2 different cases that led to 2 different expressions. When we assumed that x was big, we got a different expression compared to when we assumed that x was small. Different terms drop out. And of course, it might be the case that neither is true. And so how are we going to tell which is going to be the case? Well, we can actually just go ahead and guess. We can go ahead and assume that x is very large, or we can assume that x is very small. And when we solve for x, if it turns out that we get a small answer, and we assumed it was small, that's good. That's logically consistent. And so that may mean we had a good guess. However, if we assumed that it was small and we got a large number, or if we assumed that it was large and got a small number, that's a logical contradiction. And so that's going to invalidate our assumption. Let's look at this equation. So we have a complicated polynomial expression under the square root, and then divide it by another polynomial expression. This is probably going to be pretty difficult to sort out algebraically, if that was your inclination. Certainly an advanced calculator can do it. Well, let's see what we can make of it. So this whole expression is equal to 0.0546. Let's start by assuming that x is large. Now, if we assume that x is large, then we can start canceling out some terms here. So if x is large, that means x to the fourth power is going to be much larger than x to the fifth or x to the fourth. So those aren't even going to matter. Likewise, x squared is probably going to be a good amount larger than x. Certainly if x is very large, that will be true. So we have the square root of x to the 8th power over x squared. And x to the 8th square root is going to simplify out to x to the 4th. So we have x to the 4th over x squared. That's just going to be x squared, when we divide it, is equal to our 0.0546. Now if we take the square root of that, we get 0.233. Well, that's a very small number, which is bad because we assumed that x was a large number. And so since this is a logical contradiction, we know that our hypothesis was incorrect, and this is definitely not the value of x. Let's instead try assuming that x is very small, something less than 1 certainly, and see if that gets us anywhere. So if x is less than 1, we have something like a fourth or a 16th, something in that vein. And so when we take higher powers of that, we're going to get a larger denominator and a smaller number. So x to the 8th will certainly be much smaller than x to the 4th. So we can get rid of our x to the 8th in this case. Now be careful comparing x to the 5th and x to the 4th. Depending on the size of x, these might actually be fairly similar numbers. But if x has a very large denominator, then dividing by that denominator an extra time might make a significant difference between these two. So if x is very small, certainly we can get rid of x to the 5th here. If x is a little bit larger, that might not work out as well. But we'll try. We'll see what we get here. So we'll assume that x to the 4th is by far larger. And then same thing down here. We'll go ahead and assume that x is larger than x squared. That might not be quite as good as an assumption as we would like, but we'll see. So now we have the square root of x to the 4th, which is going to be x squared over x. So we have x squared over x is equal to our 0.0546. X squared over x is just going to be equal to x. So x is equal to our 0.0546. Now this is a small number, just like we assumed in our hypothesis, and so this all checks out. There's no logical contradictions. Now if you actually punch this expression up here into your calculator, then the answer you would get is x is equal to 0.056. So that's fairly close. It's not as close as some of our other answers. We start varying a little bit in the second digit. And the reason we start varying in the second digit is because these quantities were just a little bit too similar. But depending on how accurate we need to be, this might be fine.